All right, so like I think I mentioned just a second ago, but just going to repeat in case people didn't hear it, is the first part we're going to talk about is actually some part of section 8, so mod 1, section 8, and then we'll lead into section 9, we'll talk about statistical distributions. Note that we're not going to cover all of section 9 today. There's a lot to cover. Normally, even if I have the whole study group, I won't cover all that stuff. So just kind of know that it will go into the next study group. And then we'll talk about also section 10, which is linear regression. So kind of like showing that map forward. So the first section again, or the section we'll talk about is section 8, which is much more focused on probability. We think about permutations, combinations, that kind of stuff. So I'm going to start sharing my screen. And note while I start sharing my screen, that should be it, that, oh good, you guys didn't disappear completely. This is all on the GitHub repo as of right now. So it should be up to date. If not, just let me know. But just know it's under probability, that stuff that we're going to talk about today. So the first thing I want to show you, this is going to be relatively quick. My plan is not to spend too much time on probability, but you guys let me know, all right? So first thing is I want to show you guys some notation. So some of you might be familiar with mathematical notation. Some of you guys might see this is like a completely different language. What is this alienese kind of stuff going on here? And that's perfectly fine. Just know that as you guys get into more and more technical parts, maybe you see in your own papers for data science, you'll see these notations and stuff like that. So it's good for you to be exposed. And of course, if you ever see these kind of things, definitely share it with the rest of the cohort, you know, like maybe some people who are familiar with the mathematics, I can help you out, you know, because generally I think when people find these kind of things, it's kind of hard to search for it, exactly what's going on. So definitely use, you know, everyone as a resource as you get familiar. But this is kind of from the curriculum, so you probably looks familiar. But this right here, basically talking about sets. And sets are basically just like a group of things. So basically a set can just be like, oh, all the animals in the universe, or all the animals on the earth, or all the animals in my backyard. That would be a set. You can have things like called subsets. So you can think of like all the animals on earth and then say all the animals that are in my backyard, like are a completely different, like not completely different sets, but they're a subset. So there's a smaller set of another one. You can also say all the animals in my backyard. So maybe all the types of animals in my backyard and all the types of animals in like Nicole's backyard or something like that. And say, all right, like, are there similar animals? Well, some might be the same. There might be the same beetles. There might be different kind of like, you know, I don't know, like different types of squirrels or something like that. Like there's all these different parts. And this is what we call like this union right here. So I'm sorry, not union, sorry, this intersection. And so you'll notice that it's upside down like U. It's a very specific looking one. But this basically means like, okay, where is that crossover? And you can think of it like a Venn diagram. So if I were to just go ahead and draw some quick circles, and I'm not using that ugly looking green, so I'm gonna use this red. So if I have like, let's say my backyard and my neighbor's backyard, okay? So you can say, okay, these are all the different animals, types of animals in here, types of animals over here, and then we have a crossover. This right here would be that intersection. Now, if we have this U right here, okay, that just means basically the union. So basically it's like, oh, I have this set right here, maybe I have this set right here, and it would just be all of this. So it would be all of mine and all of this. It's like the neighbor's backyard. And note that I kind of wrote this like crossover. When you're doing a union or even an intersection, the sets don't have to have any crossover. They could just be completely different, right? So for example, it could be all the animals that start with the letter A and all the animals that start with the letter B. Well, the intersection of that, it's nothing. And that's what that circle with a cross through it like that, that means the null set. Basically, there's nothing in there. It's an empty set. So sometimes you'll see it denoted like this with curly braces. Okay, so basically there's nothing in there, right? That would be the intersection. But we can also have the union, which is basically just A and B. And you can see here, probability of A plus probability of B. So just know that's the different notation you can do, okay? And also note, one thing we do, it's not really set, this is more like probability. Usually our notation with this capital P like this is that we're saying the probability of. So when we say P of something, like the probability of A, that's kind of like saying, what's the probability of A happening or the events in A happening? And that's what we call like an event space or an event set, okay? So any questions on this notation for sets or union, intersection, empty set? Cool, sound good. All right. So next thing I want to show you is, again, this funky math notation, which I don't know how familiar. This kind of thumbs up. Who's familiar with this notation? Who's not familiar with this notation? Who's like, I don't know. Okay, good. So I see some thumbs down sideways. Okay, so I'm just gonna kind of read you this Mathanese kind of stuff. And this is very, very common and how we write things. Again, Mathanese is not a real language, but I just wanna make sure you guys all know that. So this right here, if you see that curly brace, when you see curly braces like that, usually you should instantly think set or a space, like it's some kind of stuff, okay? So what this is right here, this is like low text message volume day. I don't even know where this is from. This is from the curriculum. But basically this is E equal. So this is gonna be the set E, all right? And it's basically saying all these things are called X. And then this line usually is read as such that. So can you guys all see this all right? It's not too small. Okay, good. So that line right there usually means like such that. You'll also sometimes see, depending on the context, as like a colon. So it might see like X colon and then like a bunch of other stuff. But basically saying, all right, it's the set X such that X, and then this member right here, I'm gonna read this off all together. X is a member of the integers. And kind of breaking this down, basically saying, okay, X, and then you have this kind of like looking E thing. It's basically like an epsilon, but it's a fancy epsilon. This E basically means a member or it's in. And then sometimes we'll have a lot of times like this fancy Z. The fancy Z is the set of integers, basically all the integers possible. You'll also see some fancy letters like this, like a capital R. And that means all the real numbers. So if you remember back to like, grade school math, when you talked about integers versus real numbers versus the rationals. Does anyone know what the rationals is represented by? So it turns out to be a fancy Q. So that's the rationals. So rationals, reals, integers. There's other things too. For example, there's the complex numbers that shows up too. But just know that these are kind of relatively common. You'll see in computer science and data science by extension, integers the most common. But just know that in mathematics, we can also have these other different main notations of different things. I guess also the one we could consider, just notice, is imaginary numbers, which is like a fancy I. Okay, so basically going back here a little bit is that we read this as X, basically the set of all X, where X is inside. So X is a member or X is in the set of integers. So to say in integers. And then there's a second separate condition here. You can read that also such that basically 0 is less than or equal to X, X is less than or equal to 20. So basically X has to be at least 0 and up to 20. So that would only include basically all the integers in here, which would be 0, 1, 2, 3, all the way to 20. Okay, and that would be the actual set E, all right? So again, down here, you can see this E right here, binge watch day. I don't remember what the data set really was supposed to explain, but it's X such that X is X is a member of the real numbers and X is greater than or equal to 6. So note that this set right here, so before here, I can say like the length of this is like 21 different numbers. In here, all the real numbers include decimals, fractions, also negative numbers, but in this case, it's just greater than or equal to 6. So this goes all the way up to from 6 to infinity, including all the little like decimals and everything like that. So if we wrote this on a number line, just kind of quickly kind of emphasize this point, is 6 and then like up to like infinity, going on forever. Usually you'll kind of say, well, it's basically all of this stuff. Okay, so this is an infinite kind of like set in the sense that you can't count. I'm trying not to like use too much of the mathematical terms. There's things like, you can count it, but like from what we're talking about, basically it's like, oh, you can think of like there's an infinite number of different things. There's a way to define basically how big an infinite that is. But just know that basically it's like, oh, you're not just having discrete numbers like this, 0, 1, 2, 3. You have 0, but you also have 1, but you also have 0.1. You also have 0.01 and so on. Okay, so, well, I guess in this case it would be like 6.0 or something like that. But hopefully that kind of makes sense. Any questions on this notation? Anything kind of went through? Again, I went through it pretty quickly. So if it's something that kind of keeps coming up again and again, feel free to ask. Don't feel like it's a stupid question because this definitely depending on your familiarity, it can be kind of difficult to like understand what's going on. Okay, cool. So next thing I want to kind of talk about a little bit, probability. So we'll kind of get into this in a second, but one thing I kind of joke around is that probability is just counting, but counting is actually really hard. So it's kind of like this weird part where like, oh, we just need to figure out how many things are possible and how many things can happen. And that's all probability is, basically saying how many things can happen and how many things actually happened, okay? And it just turns out though, to count all those parts can be kind of difficult. And that's why I think, especially when you talk about like permutations, combinations, it can be kind of it's hard to figure out exactly what that number is if you're not familiar with what it's supposed to look like. So just kind of be aware of those kind of things. So I'll get back to this in a second, but I did want to point out this law of relative frequency. This is, well, I guess this part right here basically saying that if we have like a coin, like I think this is a classic example. If you have a coin and you flip it twice and you get heads twice, you know for sure that that head is completely fake and that you should never trust that coin, right? Of course not, right? You know that you can flip a coin twice and get heads twice. And so the idea here is that if I flip the coin twice, the probability of me, that sample space of me actually getting heads was 100%, right? But if I flipped it another 10 times, I probably would get closer to like, 50%. Probably not exactly 50%. In fact, if I flipped it 100,000 times, I still wouldn't probably get exactly 50%. And so the idea here, the law of frequency, and it's basically like the law of like what we assume probability is true, is that if we increase this n, which is the number of trials, so if we do it for an infinite number of time, eventually we would get to the true probability p versus the sample probability, okay, s. Okay. So this is kind of an important part. And again, hopefully, just real quick, does anyone have, does everyone understand this notation right here? This limit of n approaches infinity? Okay, so this is important because this will show up again and again and again. This should be from like calculus, but if you're a little rusty, just know that basically when we do like that limit of, some number like n approaches, this could also be like 0, -1. It could be whatever number you want. Usually we talk about infinity or negative infinity. Basically it's saying if we keep increasing n, what does that look like? So again, this is something that's very common in the technical stuff that we'll do. All right. So any questions on any of that stuff I just talked about for notation? Cool. All right, so moving right along. Okay, and so now we are going to talk about combinatorics, all right, which is always a really fun word to say. But main thing about combinatorics is basically it's us counting. That's all it is. Like it's just figuring out how many things are there. And so again, it's simple in that sense, but can be very difficult. I used to have a math teacher who we would ask her and say, is this test hard? And she'd be like, well, hard is relative, And of course, like, okay, we all rolled our eyes. But like she had a good analogy to us, walking upstairs, like walking up a stairs, unless, as long as you're perfectly able-bodied, it's not necessarily a hard thing to do, right? But if you were to walk up, 50 flights of stairs, well, that becomes more difficult. But it's not because walking upstairs itself is hard. It's just because there's just the sheer number of it. And maybe, for example, if you're doing things more complicated, the idea is like it's just more of it. And that's kind of the idea of like what this counting is. So I'm going to go into event spaces. So the first thing is that event spaces, all it is just what is possible. Okay. For example, I'm trying to think of something good. Like if I were to measure the probability of me, or just saying like, how fast can Victor get to, how far can Victor go from right now within the next 1 minute? And, technically all possible things, I could run, I could walk, I can get this within the sphere of area kind of deal. Or no, I guess a sphere because I can go 3 dimensions, but like just kind of goes like, oh, I can jump, within a minute or whatever. I could technically maybe somehow gain superpowers where I can travel the speed of light and like go over. Now, depending on what your view of reality is, like, maybe that's not true, but there, at a certain point, it's like, well, you can't go faster than the speed of light if we put these restrictions on there. So like, this is the farthest I can actually travel. And that's my event space. So this could also be true for like, continuous stuff. Okay, so simple one is just rolling dice. So I just want to show you guys a couple of ways we can code this and what this looks like. So the simplest one, a die, right? A 6-sided die, I should say, can be rolled, 1, 2, 3, 4, 5, 6, right? And that's my whole event space. Not exciting at all, right? One, I don't know, maybe it's exciting to you, but I think you're kind of boring if you think it's exciting. But we have our die roll here, 1 through 6. That's our whole event space. If I wanted to roll 2 dice, right, what I could do is I would roll 1 die, right, and then roll another die, right? And so I can actually kind of simulate this, kind of put it. You could technically, like the curriculum does, write every, like, all right, I can roll 1, and I can roll 1, and roll 1, and then a 2, then a 1, and then a 3, a 1, and a 4, and a 1, and a 5, and 1, and 6, and then go, all right, I roll a 2, and a 1, and 2, and a 2, and so on, right? And again, if you like typing, I guess you could do that, but we're programmers, so look how much less typing I have to do. I have to do more thinking, but less typing. So the idea here is, like, I have a die roll, and basically say, all right, I roll 1 die, die 0. So I'm gonna roll my die 0, and I'm like, all right, I get a 1, because it's just gonna go in order, right? So I roll a 1, and then once I have a 1, say, all right, and let me go ahead and roll my second die, right? So I have my 1, and I roll my second die, okay? And all I do is just add it to my events space, and say, okay, I rolled my second die, it was a 1. I roll my second die again, it's a 2, and I still have my first die as 1. So basically I have 1, 1, 1, 2, 1, 3, 1, 4, and then once I reach all the possibilities for this die, I'll now be able to roll again for my second one. And again, when I say roll, I really just mean saying, oh, we're going to assume this is 1, this is 2. It's not actually random. It's just kind of just rolling the same thing over and over again. So if I roll this now, that was really quick, 3 milliseconds, and you can see the length of 36, which you can probably figure out, oh, there's 6 possibilities times 6 possibilities. So I have, like, the first one has 1, 2, 3, 4, 5, 6 possibilities. Sorry, I'm doing sign language here. 6 possibilities, and then for each of those possibilities, there's another 6 possibilities. So this one has 6 possibilities, this one has 6 possibilities, 6, 6, 6, everything like that. And I can now do 6 plus 6 plus 6 plus 6 plus 6, so 36, if I counted that right. All right, pretty straightforward. So now I can roll 3 dice, right? So same idea here. I can just roll 1 die, 2 dice, then 3 dice. Same idea. I roll 1, I hold it steady, roll the second one, hold that one steady, roll a third one, do that 6 times. But now I have, for each of those 6 possibilities, I have 6 possibilities. And for each of those 6 possibilities, I have another 6 possibilities. So it turns out to be 6 times 6 times 6. And so if I actually count this out, you can see, I think it's 216. Yeah, so 216, okay. So again, it's just 6 times 6 times 6. So 6 times 36. Another thing we could have done, just to kind of prove my point, is that it doesn't really matter how you count it, is that we could have just rolled we can get the dice from our 2 rolls. So we roll 2 dice, and then we roll 1 die. So the first one, for example, might be 1, 1. And then we can roll another one. Well, that's 1, 1, and then 1. And then hold that 2 again, 1, 1, and 2, 1, 1, and 3. And of course, if we do this, we get the same answer. Okay, and that's just to prove you the 3 rolls out is the same exact thing. Okay, and again, if you wanted to just look at this, what this looks like. Really long, but you guys get the point. Okay, and again, this would be awful to write, so that's why we program it. Okay, any questions on what this looked like? Anything going on? And again, if you notice how they structured it, it just depends how you think about it. That's kind of what I'm going on. I didn't say, like, go into the code and say, like, oh, like, what's the way to simulate this? I just kind of, like, said, well, how would I count this out? Well, I'd hold the first one constant and then roll the other dice 6 times and then move on to the next part. So hopefully that kind of, you can see that logic going on there. All right, so I'm gonna move on to some math notes, some factorial. So hopefully this feels pretty familiar. Kind of fun fact, factorial is actually, I wrote a little paper. It's not really a real paper, but like for my bachelor's thesis for math, technically, I wrote factorial, but it turns out factorial is based on another function called the gamma function, which is really fun and exciting, but we're not going to talk about it because we don't need to. But just know that factorial can actually expand to not just integers, but can also be expanded over to decimals, and then actually to complex numbers like imaginary numbers and all that. And it got some really cool functionality. Anyway, it's called the gamma function. With this guy. But anyway, the main thing that you guys cared about is that you basically have factorial, and you can say, all right, this n factorial basically is n times n minus 1, so on all the way through 1. You'll notice that I'll not write the 1 because 1 times anything is just itself, right? So I don't usually write the 1, but just know technically the 1 is there. If I do 1 factorial, it's 1. Does anyone know, this is actually kind of important because it could come up. Does anyone know what 0 factorial is? Oh, good, I see Giovanna, 1, yeah. Okay. If you knew the gamma function, you would know this now. So anyway, is that 0 factorial is 1. You can actually do this you can expand it out further, like I said, by using the gamma function. But for our cases, 0 factorial will be defined by 1. There's a few reasons why. I won't get into it right now, but know that it is true. All right, so right here, I just have kind of definition of factorial. I actually don't remember if the curriculum asks you to create this or they show this for you. I don't remember for lab. So if it's for the lab, I guess you have an answer, right? But basically here, I have integers to multiply, and I'm doing some fancy stuff, which is called numpy.arrange. Okay, and basically it's like a range. It's creating a range of numbers, basically starting from 1 to n plus 1. And that way, normally it starts from 0. So that's why I'm going from 1 to n plus 1. So I have basically in this, this part right here. So if I were to do, just to show you guys that this does actually do something interesting. Let's say I do like to 5, you'll see it's a range 1, 2, 3, 4, up to that last one, 5, right? So that's why I do an n plus 1. So right here, I basically create this range of numbers, okay, this numpy array. And then because it's a numpy array, I can kind of cheat and say, all right, cool. I can just simply do this thing called np.product or .prod. Note that product is going to be deprecated. So don't use .product if you find old code, but it'll warn you if you did. But basically what this will do is say, all right, go take all these numbers and just multiply them in. So whatever this array is right here, just multiply each number through. Okay, that way I don't have to write it out myself because again, I'm lazy. I don't want to write all that stuff. And you can see here, just to prove it, when I run this function, it'll say computed n factorial is equal to answer. And that's just using an f string. Okay, and you guys have seen f strings at this point, right? Yeah, just know they're fancy strings.
Sorry, Victor.
Mm-hmm.
Yeah, how's that different to range, the normal range function?
Oh yeah, so range will create something, this is kind of getting more Pythonic, but when we use range, like just regular range, it creates, like, I'll show you this real quick. So if I do like this, you have this function, or this representation, which you notice is not a list. I could convert it into a list like this. But basically, to kind of say what this thing is doing, this range is an iterable. That's the technical term. It basically allows you to say, all right, if I do, for example, dot next, I can actually pull, oh, well, I can't do that. But you can basically say, you can pull out the next part. And so it's kind of you can iterate over it. It's kind of like a list, but it's kind of like a more general list. When I do an NP arrange, it just automatically creates a NumPy array for me versus range. I'd have to convert it into a NumPy array like this. I could do it like this, and that'll give me the same answer. Note that technically this is probably slower than this right here. In fact, you can kind of see, well, let's see. Well, okay, I'm not going to go into that, but trust me that it's probably slower because this uses some efficiencies, but it's essentially the same thing if I just wrap it with an array. Cool, cool. All right, so moving on then, good question. Okay, I have my function here, okay, and so I do the factorial of 5. Does anyone know what the factorial of 5 is? I just slept, 120, all right? So basically it's just 5 times 4 times 3 times 2. We don't need the 1, all right? So know that we have this possibility here, or we can do this really easily. We can also, just to kind of show you, we can do factorial 8, which is, of course, 4,320 or 40,320. So you can see this number gets very, very big, very, very quickly. But note that we also could have done 8 times 7 times 6 times 5 factorial, because 5 factorial is just 5 times 4 times 3 times 2 times 1, right? So again, you can see we get the same exact answer. Kind of a fun fact is that, again, if you try doing this with a calculator, and this is something to be aware of, if you try, it'll probably cut off at a certain point depending on the calculator. Google's calculator, so if you Google, you know, like the equal sign and put in the Google calculator, it goes up to 170 factorial, which is about 10 to the power of 306, which means 1 followed by 306 zeros. So it's over a Google, it's like a Google to the power of 3. So pretty big number. 171 factorial, I tested this out myself, does not work. It basically just gives infinite, which is not infinite, but just know that you can't, it won't do any more than that. Now, if I do something similar in here, if I try doing 25 factorial, you can see very large number. Okay, I'm not going to even try to read that, right? If I do, actually, I think I showed it up to 26. Again, this is what I do in my spare time, right? 26, you'll see, oh, negative 156. Wait a second, negative. That doesn't work out. And the reason why it turns out to be computers have a limited amount of memory. We won't get into that, but basically just know that computers only have so much space to save a number. And that basically is that when we try to go past certain point, basically the computer numbers essentially wrap in on itself, which is really interesting. When you get into floats and stuff like that, like decimal numbers, it is even more complicated. But just know that at a certain point, your factorial will not work. Either, depending how you calculate it, your computer is going to crash trying to calculate it, or more likely you'll get an error like this, okay, which is like an overflow error. Okay, so kind of fun. Be aware of this kind of stuff. But note that I could have done 26 minus 1, and that would be fine. But if I try to do, I'm trying to think of a good way to do this. Oh, I guess I should show this part because I didn't actually write this down. If I do like 5, oops, that's not what I meant to do. 5 factorial divided by 4 factorial, okay? Well, that's just simply 5 times 4 times 3 times 2 times 1 divided by 4 times 3 times 2 times 1, right? But of course, we can divide. So this actually all goes 1 divided by 1 is 1, 2 divided by 2 is 1, so on. This basically just simplifies to 5. Okay, so just to prove it, again, is if I do factorial. Oh, this is because it's a list or a markdown. If I do factorial of 5 divided by factorial of 4, I should just get 5. See that? Okay. Note, however, remember I said like, oh, you can do like 26 divided by 25, right? We know that should, if you do the numbers, it should just be 26, right? Because we basically divide everything out. But of course, it's not going to do that. It's going to give us this weird number here because 26 factorial is this. So just be very aware of this kind of stuff that, that if you put your numbers directly in the calculator like this or the computer, it might give you the wrong answer because of overflow errors. Okay, so it's a subtle point. Any questions on this? Okay, cool. And if you're curious about this, I can send you guys some resources that kind of explain a little bit why this happens. Interesting, but not super important for us right now. Okay, so the reason I talk about factorials, yeah, I'm seeing what time it is. Okay, I'm running a little bit low on time. The reason why I talk about factorials is because we talk about permutations and combinations. And main thing about permutations, you'll hear the word permutations said over and over again. It's basically just saying how many ways can you arrange a group of items. So for example, if I have the letters A, B, and C, okay, if I have those 3 letters, say how many ways can I rearrange this? Well, your strategy might be something along the lines like, well, okay, let me do oops, I'm not gonna use that. Sorry guys, I had a new mouse, I'm like not gonna use that. But the first thing I'm gonna say, well, let's start off with the letter A and then like figure out what the next 2 letters are. Well, okay, that could be either B and then it would be C, or it could be C and then B, okay? So that would be 2 possibilities, but of course that's only with A being first. So what if I had B first? Well, I could have then, you know, AC and then CA, okay? And so you kind of get the point. So you can see here, the last one, just to kind of be complete, is C, and then it could have been AB or BA, which we can see here, there are 3 possibilities here. They're basically 3 groups. I could either start with A or B or C first. And then in each of those groups, I have 2 more groups going on here, right? Okay, and I could technically say there's, at the very last one, there's 1 group for each, but again, 1 doesn't matter, who cares about 1? So basically, if you look at this, oh, that's basically, there's 3 groups, but each group has 2 groups. So that means it's 3 times 2 times 1, because 1's lonely. And that's the same thing as just saying 3 factorial. Okay, so really that's what a permutation is. And that's actually why we can actually say, oh, there are 3 groups, 3 factorial groups. Or we can use 3 factorial to say that's the total number of groups there, okay? I guess that's, okay, yeah, I'm gonna go with that. So this is one way we can kind of create these different like permutations, stuff like that. Now, kind of looking ahead is that we do have a formula, and I don't actually recall, no, the curriculum does write this, is basically permutations, NK. Everyone has a different way of writing it. Note that you'll see in so many different ways. You'll have this n factorial divided by n minus k factorial. And I always say, try not to memorize this because you'll probably memorize it wrong unless you do it 50,000 times. And then even then, who knows if you'll actually mess it up. But know that this is kind of a generalized way. So what this actually means is basically saying, all right, you have n number of items. Let's say we have 4 items, A, B, C, and D, okay? And we want to arrange it in k different ways, okay? And let's say basically how many spaces do we have available for all those spaces, right? Well, if we have just simply 4, let's go one back. Let's just do A, B, C, okay? If I say, oh, there's 3 spots, okay? Well, that means we saw before that was a total of 6, 3 times 2 times 1. Well, if we put in this formula here, that would be 3 factorial divided by 3 minus 3, which is 0 factorial, which remember I said 0 factorial is 1. So that just means this is 3 factorial or just simply 6, okay? So that's kind of like, that would be like our first part. So that's pretty simple. That's what we just saw. But now we have something more complicated. Let's say we have something, like I said, A, B, C, and D, and we have only 3 spots now, okay? So you still do the same thing. You basically say, okay, well, the first spot can have A, B, C, and D, right? And so once we use one of those spots, right, what do we have left here? Well, we have, if we use A, we only have 3 other choices, right? B, C, or D. And then if you had B, we'd only have C, D, A, right, and so on. So basically, for each spot here, we had 4 choices. Here, we only had 3 choices. And last part, we had only, well, if you realize this, we used 2 already. We only have 4 total. We have 2 more choices after that, okay? So that's just simply 4 times 3 times 2. And if you looked at this formula, if you remember this part, you could just simply say, oh, well, that's n is 4 factorial divided by 4 minus 3 factorial. Is that right? Yeah. Okay. And that would just be 4 times 3 times 2 times 1, well, divided by 1. So that didn't really help us out. But trust me that if we had something like, let's say, only 2 possibilities, right, we can just see, oh, there's only 4 times 3 possibilities. So this would be 2. And we would have 2 factorial, which is just 2 times 1. So we can divide out the 2, divide out the 1s, get 4 times 3. So this is where this formula is coming from. This is why I say, like, try not to memorize this formula. That's not the important part. This is the important part. Understanding where this is coming from so you can build this. This is nice once you realize what the pattern is, because once you know what the pattern is and you realize how it's tied, you can say, okay, what if we had like 100 different letters and then we had, you know, only 4 spots? Well, okay, then you can just simply say, what's 100 factorial divided by 100 minus 4, which is 96 factorial. Okay, and instead of calculating that part out, you're smarter than this, right? You can say, oh, just that's essentially everything's going to be divided out except for 100, 99, 98, and 97. And you multiply those together and you have your answer. So this is kind of like understanding this part, though, with the different spaces is more, I think, is more important than actually recalling the formula. And this is what's going to, trying to pull out the formula is going to be the tough part in the sense that like it's going to trip you up. Okay, so that's kind of how we create these permutations. Any questions on that? Okay, thumbs up, sideways, thumbs down. Okay, cool. Okay, you guys got it? All right. And of course, if more questions come up, always ask, you know, either now or in the future. So I'm going to talk about combinations, but I'm actually going to use the same space, kind of thinking about that. And I'm going to show you the formula first. And you'll notice here, it's essentially the permutations thing divided by k factorial. And the reason why is because combination says we don't care about the order, essentially. Basically, if we have ABC and CBA, it's the same damn thing, right? That's essentially what's going on. And so what happens here is like we essentially say, well, okay, if you think back, in our, I'm gonna write this small example, ABC, ACB, CBA, CAB, right? And then we had D, or not D, adding new letters in there, BAC and BCA, right? What we can see here is that if we don't care about order, well, that means, okay, like, Yeah, if we don't care about order in that case, we don't have as many possibilities, right? So we can actually get rid of most of these kind of things. And so in the case of like this 3-part right here, we say, oh, there's 3 parts. Well, 3 factorial. So basically, if you say order doesn't matter, how many options do we have? 1. Good. Trick question, right? It's only one possibility, right? It doesn't matter what order we put them in. It's all the same letters. And you can see this formula happens. We saw this n factorial, which was, well, I'll just write it out here, was 3 factorial, right? Divided by 3 minus 3 factorial, divided by 3 factorial. Well, we know this right here is going to be 1 factorial, or 0 factorial, which is just 1, okay? 3 factorial divided by 3 factorial, oh, that's just 1, right? That's all that's telling you right there. So essentially this guy right here, that k factorial factor, is telling you how many things are you double counting? How many things are you considering? So going back to one of our examples with the 4 different letters, but only, let's say 3 spots, right? So k is equal to 3, okay? So again, we had all these different possibilities. I think the total ended up being, what was it, 12? No, 24 possibilities, 4 times 3 times 2. Right? So if we had 3 different spots, okay, 3 different spots, and we had 4 different letters, we can put those letters in certain order, and we'll have 24 different orders. But because we don't care about order anymore, we have to divide out our copies, basically. Like CAB is the same thing as ABC. And we just simply divide it by this k factorial, which turns out to be just 3 factorial. Okay, so in that case, 3 factorial is 3 times 2, or you can think of it, well, however you want to think about it, right? So 3 factorial is 6, so we can just simply get, there's only 4 possibilities, okay? And that way you don't have to go through all of the different drawing out stuff. And this is the kind of stuff that you kind of apply each time, all right? All right, so that kind of ends what I want to talk about, combinations and permutations. One thing I was thinking, let me ask you what you guys think real quick, is I'm thinking of continuing this conversation for Friday. And the reason why is because I can go on more about some examples, and maybe we can do some examples, for example, on Friday. For example, I can say, like, if we have different number of colored balls, for example, if we have 3 identical red balls and 2 identical green balls, how many ways can we organize like this information? Okay, and I was thinking we can talk about this and say, well, okay, this is a little bit different from what we've seen so far, and I think it's similar to like what we've seen in the curriculum. There's another one, for example, all these great examples for like how many, if you had like 5 consonants and 4 vowels, you know, and we structure in a certain way, how do we apply to this? I think this is something we could go, you know, a little more explanation if you guys are wanting it. But I think right here, I'm going to kind of cut it to go to statistical distribution, so we can start section 9. How do you guys feel about that? Thumbs up? Okay. Just quickly, if we are going to put Friday partly like to do some office hour stuff, would you guys be interested? Just thumbs up if you're interested in doing this on maybe a Friday. Okay, see thumbs up. Okay. See some nods. Okay. Not as many enthusiastic, maybe some sideways and stuff like that. But that's fine. Maybe we'll commit. I'll ask you guys on Slack too and say what you guys are interested in. We'll see what happens. But I think I'm going to save this. Maybe we can discuss it for another time.